Hey everyone, welcome back to the paper 4 series of physics 9702. Today we're going to talk about physics paper 4 variant 42 from the major in 2024. 2 days ago, I think yesterday, sorry, we did the 4.1 and 4.3. All right, so as always, before we dive deeper into this paper, let us show you what we can help you with for your exam preparation. This document, which is available on our Patreon, along with the other A2 uh, packs also, we have named this as Grade Booster Pack because it's going to help you with the theory part, with the derivations, with the graphs, and everything that is very frequently asked, especially those that are frequently asked. So for this one, for example, you have the syllabus points on the left-hand side, questions, answers relevant to the marking scheme, and their years. So for example, over here, you can see the questions over here that are very frequently asked. So you will see a lot of years on the right-hand side. Their definitions and the reasons align with the marking schemes. Second thing are the derivations. We all struggle with derivations once in a while, so we have got you covered. These include the derivations listed in the syllabus and the ones that are asked again and again. This is single most important resource that we have, almost on par with the FAQs. We all know our students struggle with the field and the potential graphs, especially with the charges, opposite charges, similarly charged spheres also. So we've got you covered. Now, this one, definitions and formulae, this is a basic rundown of the major terms and their formulae, whatever, however you want to do your revision. Now, this again is all available on our Patreon. The link will be in the description. So don't wait for the exam day. Get it today. Now, define the radian. So just to show you how you can actually leverage this grade booster pack. So this is unit of angular displacement where 1 radian is equal to angle subtended at the center of a circle by an arc that is equal to the length of the radius of the circle. So that's all we have to write over here. So SI unit for angular displacement where 1 radian is angle subtended at the center of a circle by an arc of length equal to radius of the circle. A circular metal disk spins horizontally about a vertical axis, as shown in the figure. A piece of modeling clay is attached to the disk. For the instant when the piece of the modeling clay is in the position shown, draw an arrow labeled V showing the direction of velocity of the modeling clay. So velocity is, it's rotating this way, so velocity would be going this way. This is your V. And showing the acceleration, acceleration is always perpendicular and directed towards the center. So this is your A. Let's make it slightly perpendicular. Yes, this is your V. Okay. Now, metal disc in figure 1.1 has a radius of 9.3 centimeter. Center of gravity of the modeling clay is 1.2 centimeter from the rim of the disc and moves with a speed of 0.68 centimeters. So this is the rim of the disk. Okay. Calculate the angular speed omega of the disk. So we know that V is equal to R omega, so we can use the same relationship, V over R. V they have given us as 0.68. R, we need to know the distance between this axis and the modeling clay. That is going to be the difference between 9.3 and 1.2. And we have to convert it into meters also. So 10 raised to the power minus 2. So 0.68 divided by 9.3 minus 1.2 times by 100. So 8.395, so roughly about 8.4. Now, calculate the acceleration A of the center of gravity of the modeling clay. So A is simply just V squared over R. V squared they gave us to be 0.68 squared. R is, we can again do the same thing. Times by 10 raised to the power minus 2 squared. So, sorry, no, not this squared, not this squared. Only 0.68 is squared. So 5.709, so roughly just 5.7. Second piece of modeling clay is attached to the disk at the position shown. Second piece of modeling clay has a larger mass than the first piece. By placing one tick in each row, complete the table 1.1 to show how the quantity is indicated compared to the two pieces of modeling clay. So angular speed. Now, for the angular speed is the same because angular speed depends on 2 pi over time period. So time period of this oscillation of this circle over here is the same. So time period for to complete uh, 2 pi radians is going to be the same for this object and for this object. So angular speed is the same. Linear speed. Now linear speed, V is equal to R omega. So if omega is the same, R2, let's call it R2 over here and R1 over here. R2 is less than R1. So if you multiply by constant omega, omega R2 less than omega R1. So this is going to be less than. Same way, acceleration. Acceleration can be found by v squared over r or r omega squared also. So even if we square this, you will have the same result. So acceleration is also less for the second object. All right, moving on to the second question. With reference to thermal energy, state what is meant by two objects being in thermal equilibrium. So thermal equilibrium means that there is no net transfer of energy and they are in the same temperature. So just to show you that we have this covered over here, so it would be beneficial if you get this and read it. So yeah, okay. When the two bodies are in thermal equilibrium, it means that they are at the same temperature and that there is no net flow of heat between them. So it means that they are at the same temperature. And since they said thermal energy, so we will replace heat with thermal energy. And there is no net transfer of thermal energy between them. Two cylinders X and Y each contain a sample of an ideal gas. The samples are in thermal equilibrium. Thermal equilibrium means at the same temperature and obviously ideal gas. X has a volume of this, contains 0.74 moles of gas, pressure this, volume this, contains, and Y, sorry, contains volume this, pressure this. Data for the two cylinders show that the temperature of the gas in X is 234 degrees Celsius. So we know that these are ideal gases, so they will obey the PV is equal to nRT. We have the moles, we have the pressure, we have the volume. R is a constant, so we just need to apply for T. T is the thermodynamic temperature, so we will convert it into Kelvin. So T is equal to PV over nR. P is given as 1.2, 10 raised to power 5. Volume is given as 0.026 divided by 0.74 times by 8.31. You can confirm the value from the booklet, from the constants. 1.2 times by 0.026 divided by 0.74 divided by 8.31 times by 10 raised to power 5. You get 507.367. This is in kelvins. So theta degrees in Celsius is equal to temperature in Kelvin minus 273.15. So 507.367 minus 273.15. So answer minus 273.15, that is 234.2, roughly equal to 234 degrees Celsius. Determine the number n of molecules in the gas Y. So they are at the same temperature, which is this one. And this gas also obeys the ideal gas. So since we need the n number, so we can use nkt this time. So they are at the same temperature, right? So n is equal to PV over KT. So P is 2.9, 10 raised to power 5. Volume is 0.043 divided by K is 1.38, 10 raised to power minus 23. Again, you can find the, you can confirm the value from that. Temperature, again, we are going to use the Kelvin temperature, that is 507.367. So 2.9 times by 0.043 divided by 1.38 divided by 507.367 times 10 raised to power 5 plus 23. You get 1.781, 10 raised to power 24. All of these numbers are in three significant figures. So we will leave it in three significant figures also. So even this, we had this. So 1.78, 10 raised to power 24. The gas in X consists of molecules that each have a mass that is 4 times the mass of molecule of the gas in Y. Explain how the root mean square speed of the molecules in X compares with the root mean square speed of the molecules in Y. Okay, so since they have the same temperature, they have the same mean translational kinetic energy. So let's write over here. So same temperature means same mean translational kinetic energy, which is half mc squared equals to 3 by 2 kT. So this means that they will have the same relationship. So mx c squared x will be equal to my c squared y. So because obviously half, and we don't need to concern ourselves with 3 by 2 kt because this is a constant and not even 1/2. So they said that the molecules uh, of X are 4 times the mass of molecules in Y. So we have 4 my Cx squared equals to my c squared y. Cancel out this. So how does this mean squared speed compare? So that is 1/4 of mean squared speed of y. So that's all we have to write over here. Sorry, they asked for the RMS speed. So RMS speed is basically the square root, square root, square root. We get the CX RMS is equal to 1/2 of CY RMS. So that's what we just have to write over here. So since both gases at are at same temperature, their molecules have equal mean translational kinetic energy so what we can how we translate this is that product uh, product capital P of mass and mean squared speed is constant, which means mean squared speed is 1/4 of mean squared speed of y. Sorry, this is double E over here. RMS speed is square root of mean squared speed. So RMS speed of X is half of RMS speed of Y. Okay, all right. State what is meant by internal energy of a system. So we can say that the internal energy of a system is the sum of the okay, so we can say that the internal energy of a system is the sum of all sum of the kinetic and potential energies of particles representing total energy of the system total energy of particles of the system, including their random motion and interactions with each other. By the way, this is also in our FAQs. With reference to molecular kinetic and potential energies, describe and explain how the internal energy of the system changes when a gas is heated at a constant volume so that its temperature changes. Okay, so two things you need to know over here. They're talking about substances that are non-ideal. So, so the internal is based on the sum of kinetic plus sum of potential energies. Also, the net change in internal energy is caused by the change in heat, additional reduction of heat, plus the work done on the system. So when the gas is heated at a constant volume, no work is done on the system, or no work is done by the system. So that means the change in internal energy is only coming from the heat supply. Furthermore, it is heated at constant volume, so there is no change in potential energy of this gas because there is no change in molecular separation. However, since temperature is associated with the mean kinetic energy of particles, if temperature is increasing, kinetic energy is increasing. So that's what we just simply have to write. Oh, sorry. So since gas is heated at constant volume, there is no change in molecular separation, meaning no change in potential energy. Potential energy of particles or molecules. Tem the temperature increases, raising the mean kinetic energy of particles and subsequently the internal energy, the net internal energy of system, of the gas. All right. A wire is stretched within its elastic limit at constant temperature. So if there's a constant temperature over here, that th- then the change in internal energy is happening from the change in potential energy. Since this is stretched, the net potential energy is risen. Okay, so that's what we have to write about. So constant temperature means no change in net kinetic energy of particles. However, stretching increases molecular separation, raising the net potential energy of particles or molecules, whatever you want to call them. Therefore, the internal energy increases. That's it. All right, moving on. A block of mass m oscillates vertically on a spring. The acceleration a of the block varies with displacement x from its equilibrium position as shown. The amplitude of the oscillations is 3y and maximum acceleration is 2a. Explain how figure 4.2 shows that the oscillations of the block are simple harmonic. So we know that acceleration is proportional to displacement, which means passing from origin. And the negative sign uh, over here indicates negative gradient. So that's what we just have to write over here. So straight line passing through origin indicates acceleration is proportional to displacement, and negative gradient shows acceleration is always directed opposite to displacement. That's it. Deduce expressions in terms of sum or all of m, a, and y for the angular frequency of oscillations. So angular frequency can come from this thing. Since this is passing from the origin, one of the points is O and O, 0, 0, sorry. Then we have 3y and minus 2a basically. So acceleration 3, sorry, no. Displacement is 3y, acceleration is minus 2a. So minus 2a is equal to minus omega squared, what was it? 3y. So minus canceled. So we have omega squared is equal to 2 over 3, 2a over 3y. So which means that omega is going to be the square root of 2a over 3y. So 2a over 3y under root. The maximum speed v naught of the oscillations. So maximum speed is given by omega x naught. So omega we have just found to be 2a over 3y under root times by x naught was 3y. So we can actually make it, we can do a little bit of algebra over here to make it, to bring it into the square root. We can make this as 9y squared. So 2a times by 9y squared over 3y. So now we can cancel a few things. So 3 times by 3, y cancels out with y. So you have 2 times by 3, 6, a y whole under root. 6 a y whole under root. Energy E of the oscillation. So total energy, you can see the from the formula booklet also. That is the maximum kinetic energy, half m v naught squared basically. We don't actually need to do this over here. So we have the v naught squared. So do we have the mass? A mass m. Okay. So half m times by 6ay because the square of that is that. So 3 am y. The period of the oscillation, 3 am y. The period of the oscillations is 0.75 seconds, and the value of 3y is 1.8 centimeter. Determine an expression for x in terms of time t, where x is in centimeters and t is in seconds. So if period of the oscillations is this, so that means omega is going to be 2 pi over 0.75. So 2 pi divided by 0.75, that is 8.378 radians per second. And this is x naught is equal to 1.8 centimeter. So determine expression for x in terms of this. So that's going to be x is equal to x naught sine omega t. So that is 1.8 sine omega is 8 point, let's say 4 t. So 1.8 sine 8.4 t. That's all we have to do. All right, moving on to the next question. Define electric potential at a point. So this is a very frequently examined definition. So let us show you over here where we have the definition also listed, will be in the definitions and formulae booklet. So electric potential is the electric potential energy per unit charge or work done in bringing a unit positive test charge from infinity to that point without acceleration. Okay, so simple thing. Work done per unit charge and bringing a unit positive test charge from infinity to that point. If we show you in the definitions also, that is also the same thing. Work done to move a unit positive charge from infinity to that point. So choose a simpler one. So it represents the work done per unit positive, sorry, no. Work done per charge, per unit charge in bringing a positive test charge from infinity to that point. Okay, so work represents the work done per unit charge in bringing a positive test charge from infinity to that point. Okay. Two isolated metal spheres x and y are near to each other in a vacuum. The centers of the spheres are 1.2 meters apart. Point P is on the line joining the centers of spheres x and y and is at a variable distance x from the center of the x. Figure 5.2 shows the variation with x of the total electric potential V due to two spheres. Now, if the potential is in the same side of the x-axis, sorry, on the same side of the y-axis, that means on top of the x-axis, that means both charges are positive charges. State three conclusions that may be drawn about this field. The conclusions may be qualitative or quantitative. Okay, just to show you what points we must look at. So we have listed over here what points you should look at when they give us a certain question like this. So, okay, yeah. So we have to look at the radii of the spheres, signs of the charges, magnitudes of the charges. So these are the conclusions that we must point out. So going back over here, as you can see, first the radii, this is 0.3, and this is 1.1 to 1.2, so 0.1. Okay, so one third. So this charge over here is one third of the radius. Okay, all right. This is one observation over here. So radius of sphere X is 0.3. So we don't have to just, describe it. We have to point out the conclusion from that. Okay, so not just description. We already know that this is 0.3, 0.1. So we have to describe it also. Like we have to draw a conclusion from it also. So radius of sphere X is 0.3 meter, whereas radius of Y is 0.1, showing radius of X is 3 times the radius of Y. Okay, now the signs of the charges. They both have the same sign of the charges. X and Y are carrying the same sign of charges. Second thing was the magnitude of the charge. Now, to understand about the comparison of the charges, you need to see how the graph of the net potential changes. So net potential over here is due to the qx, distance from x, plus kqy, and 1.2 minus the distance from sphere x, center of the sphere x. So we can't directly deduce the potential over here because due to the effect of neighboring conductors, the potential does change. So if they are the same sign of charges, the potential will slightly be raised at the surface. So that means we cannot deduce the comparison of charges from that case over here. What we can do over here, there are two ways we can do this. We can look at the minimum point of potential, or we can look at the graph over here. If we can somehow show a relationship that the weight, like the skew of the graph is symmetric. It is not skewed. The graph is actually symmetric between this and let's say this point over here. So the graph is symmetric over here. So this is 0.3, this is 1.2 minus 0.3. And as you can see, the value is the same. Same case with at 0.8, this. Now, logic dictates that as you go further, like as you compare this, 0.6 would be the point where they both have a common value. Oh, sorry, where they have a minimum value, where the minimum value is 0.6. And this can only happen if the charges are the same magnitude also. Because we're saying that the F due to x, force due to x is equal to force due to y at x is equal to 0.6 meters. So force is kq over r x. Sorry, let's go with x now. Let's go with 0.6 squared now. This is x kqy over 1.2 minus 0.6, so 0.6 squared. So this cancel, this cancel, this cancel, this cancel. So obviously this means that qx is equal to qy. So how do we actually write about this? We say that the magnitudes of charges on x at y and y are same because minimum potential and therefore zero electric field strength occurs at 0.6 meters. Now, a proton is held at rest on the line joining the centers of the spheres in B at the position where x is 0.6. Proton is released, described, and explained without calculation the subsequent motion of the proton. Okay, so first off, we have already said that at this point, electric field strength is 0. That means if you put a charged object over here, in between over here, it will be, this is, since we're talking about a proton, it will be pushed this way by x and pushed this way by force y. So at this point, the forces will balance themselves out. So they will balance each other out. So there will be no force, no acceleration, no motion. If we look at the potential graph, so if we place a positive charge, it will follow the potential gradient. It will go down the potential gradient. So if we place it over here, it will go down the potential gradient. If we place it over here, it will go down the potential gradient. Over here, this is already at the minimum point. So it does, so to move it to this point or to this point over here, we will have to provide energy. We will have to do the work done against the electric field. So different ways to say this, that the electric field strength is 0 at 0.6 meters. So no motion in any direction would occur. That is because to move in any direction further would require energy, work to, energy or work to move up the potential gradient. That's it. All right. Two capacitors X and Y are connected in series to a power supply of voltage V as shown in this. Capacitance of X is Cx, capacitance of Y is Cy. Derive an expression in terms of Cx and Cy for the combined capacitance Ct of the capacitors in the circuit. Explain your reasoning. So we have to derive it. So we know that using Kirchhoff's first law over here, actually, sorry, the second law, the in the closed loop, the potential differences will add up. So using Kirchhoff's second law, V is equal to Vx plus Vy, where Vx is equal to charge on X over Cx, and Vy is Qy over Cy. Since it is a series circuit, Ix is equal to Iy, which would mean Qx is equal to Qy. Therefore, V is equal to Q over C effective equal to Vx, which is going to be Q. Let's make it equal to Q over Cx plus Q over Cy, which further means when you cancel out Q, 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 simplifying yields 1 over C effective, total capacitance. They give it as total capacitance So CT. So CT is going to be equal to 1 over Cx plus 1 over Cy. All right, two capacitors P and Q are connected in parallel to a power supply voltage. The capacitance of P is 200 microfarad. Capacitance CQ of Q can be varied between 0 to 400 microfarad. When CQ is equal to 0, total energy stored in the capacitors is 2.5 millijoule. Show that the supply voltage is 5 volts. Okay, so we have this over here, V, and this is connected to P and Q. So this is P and Q. We know the total capacitance now. So C total capacitance would be Cp plus Cq. So total energy that is stored is going to be equal to half C V squared. So in this case, this is your total capacitance or effective capacitance. So half Cp is 200 microfarad because Cq is 0 right now. V squared and energy is 2.5 millijoules. So voltage square would be 2.5 10 raised to the power minus 3 times by 2 divided by 200 times by 10 raised to the power minus 6. So square root of 2.5 times by 2 divided by 200 times by 10 raised to the power minus 3 plus 6, you get 5. 5 volts. Now, calculate the total energy in millijoules stored in the capacitor when CQ has its maximum value. So maximum value will go up to 400 microfarad. So E is equal to half C total V squared. So half C total is going to be 600 microfarad. Voltage squared is 5 squared. So we have 0.5 times by 600 times by 25 times by 10 raised to power minus 6. You get this value. So 1, 2, 3, so 7.5, 10 raised to power minus 3, which is that total energy. So on figure 6.2, sketch the variation of the total energy E stored in the capacitors with CQ as CQ varies from 0 to 400 microfarad. So it starts off with 2.5 millijoules. Oh, sorry, this is going to be 7.5 millijoules. So this is joules, so this is going to be 7.5 millijoules. So it starts with, it starts with 2.5 and it goes to 7.5. Simple. So starts with 2.5, 407.5. That's it. All right. State Faraday's law of electromagnetic induction. You can say it states that the EMF induced in a conductor is proportional to the rate of change of magnetic flux linkage. That's it. Figure 7.1 shows a coil at rest at a uniform magnetic field that is parallel to the axis of the coil. Coil is connected to center 0 voltmeter. Flux density B of the uniform magnetic field varies with time t as shown. Coil consists of 340 turns, each of cross-sectional area 3.2, 10 raised to the power minus 4. Calculate the maximum magnetic flux through one turn of the coil. Okay, so what we can do over here, since they said one turn of the coil, not the 340 turns, so we just have to use the BA. So when they ask for the entire coil, then we multiply with 340. So maximum, sorry, uh, in this case over here, so phi max will come from B max times by A. So B max is, okay, let's see what resolution is. So 4 is divided into 10, so 0.4, which means that this is 4 minus 1.6. So 0.4, 0.4, 0.4, 0.4, so 2.4. Okay. Oh, no, sorry. No. So, and this would be 8 minus 0.8, 7.2. So 7.2 is responsible for that. So, and also this is millitesla. So 7.2, 10 raised to power minus 3 times by 3.2, 10 raised to power minus 4. So 7.2 times by 3.2, 10 raised to power minus 3 minus 4. We get this value. We need it in the standard form. We get 2.304, 10 raised to power minus 6. So 2.3, 10 raised to power minus 6. All right, moving on. Determine the maximum rate of change of magnetic flux linkage in the coil. So basically, they're asking us about the maximum EMF that will be generated. So maximum rate maximum EMF, basically they're asking us about the EMF maximum. So you can write about the EMF maximum is going to come from the NA, because these things are constant, the maximum change of, maximum change of magnetic flux density over time. So all we need to find out is what's the maximum rate of change over here. Now, there are two ways to do this. One is a little bit mathematical way. The other is, tangent way. So basically, we have to draw a tangent at the steepest point. So steepest point is not obviously these points. These are the 0 points. This is where the gradient is 0. Steepest points are at their mean positions, where the sine or the cos positions. So that's what we have to do. First, we need to find out where is the mean position. So all we need to do is do 7.2 plus 2.4 divided by 2. So 7.2 plus 2.4 divided by 2, that is 4.8. So that means 4.8 is the mean point, mean position over here. So let's draw a line at 4.8. So 4.8 is this one. So this is the mean position for the graph. Now we need to draw a tangent over here. So we will choose a different color for this. Let's choose green. And we need to make a line through this. So So what we do now is take 2 points and find out the gradient between them. So one point is obviously this one, which is, if we notice, 0.5 and 4.8. The other one, this one. This one is clear. That is 0 and 1.2. Okay, so I'll find the gradient first and then move to the equation below. 4.8 minus 1.2 divided by 0.5, that is 7.2. All right, so uh, so what we do over here further now, we need to take 2 points and find the gradient. So one point is this and the other point this. Now let's mark down what these points are. So this one will be 0.5 and 4.8. This one is 0 and 1.2. Fuck. So now what we do further is we mark 2 points for the gradient. So one point over here is this one, which is 0.5 and 4.8. And this one over here is 0 and 1.2. So I'll note down this in the calculator before I forget this. So you have 4.8 minus 1.2 divided by 0.5 minus 0. So we get 7.2. Okay, going back. We have number of turns was 340. Area was 3.2, 10 raised to power minus 4. And the gradient is 4.8 minus 1.2 divided by 0.5 minus 0. So 340 times by 3.2, 10 raised to power minus 4 times by 7.2. We get times by 340 times by 3.2, 10 raised to power minus 4. We get 0.78. Since this answer depends on us taking a gradient and the values over here will differ from student to student. Slight variations are acceptable over here. So although the marking scheme has given 0.2 as the correct answer, but for the following uh, questions, following parts, they have let it, they have already clearly stated that we will be using the value that we find over here. So it doesn't matter if your answer didn't come out to be 0.82. State the maximum electromotive force. Basically, this is the potential difference or EMF induced. On figure 7.3, sketch the variation of EMF V induced across the coil. Okay, so we know that the maximum and the minimum voltage would be 0.78, but in what places? In what times? So we see over here that at wherever the gradient is steepest, that's where it's happening. So 0.5, 1.5, 2.5, 3.5, and so on. And wherever the gradient is 0, wherever the turning points are, that's where it's going to be 0 voltage. So how we can actually make this is you have 0 over here, maximum over here, 0 over here, maximum, minimum over here, 0, minimum, maximum, 0, minimum, 0, maximum 0, minimum 0. So all we need to do is to make a line. So make sure your peaks and troughs are rounded. They're not sharp peaks. So two more waves. That's it. All right, the variation of V with T can be described by V is equal to A sine B T. So A, we know that whenever we have a sine function, this is the amplitude. This is the amplitude, and B will dictate the period. Actually, this is, sorry, no, no. This is the angular frequency, which dictates period, basically. So amplitude is V naught 0.78, and B is your omega 2 pi over 2 milliseconds. However, since V is in volts, the time or the angular frequency should be written in radians per second. So to do that, we divide this by -3. So we get 1000 pi. So 1000 pi, we get 3141. So roughly about 3100 radians per second. Okay, all right, moving on. Figure 8.1 shows the part of the emission spectrum of the visible radiation emitted by hydrogen gas in a star in a different galaxy. The galaxy is moving away from Earth at a speed of 6.2 10 raised to power 6. Explain how the positions of the lines in emission spectrum seen by an observer on the Earth differ from the positions shown in 8.1. So basically, this is due to the Doppler effect. Doppler effect, or more specifically, the redshift. So we can explain it in that fashion. So wavelengths observed on Earth will be higher due to the Doppler effect. Instead of Doppler effect, you could alternately say redshift caused by star receding relative to the Earth, or moving away from the Earth. On figure 8.1, draw three lines in possible positions in the spectrum seen by the observer. So notice one thing over here, this is increasing frequency. So that means this would be the increasing wavelength. So wavelengths we can draw over here, over here, over here. The lines in 8.1 correspond to electron transitions down to the energy level minus 3.40 electron volts. One of the lines represents the emitted radiation of the wavelength 488 nanometer. Calculate the energy of the photon of this radiation. So basically, E is equal to hc over lambda. So 6.63 10 raised to power minus 34. Planck's constant value can be found in the constant sheet. 3 10 raised to power 8 divided by this lambda should be in meters, not nanometers. So 488 10 raised to power minus 9. So 6.63 times by 3 divided by 488 times by 10 raised to power minus 34 plus 8 plus 9. You get this value 4.075 10 raised to power minus 19, which you can write it as, since the values that we have are in three significant figures, so 4.08 10 raised to power minus 19. Determine the energy in electron volts of the energy level from which the electron transition originates to cause the emission of this radiation. Okay, so first off, what we would need to do is we would need to convert this into electron volts. So photon energy in electron volts. So 4.08 10 raised to power minus 19 divided by 1.6 10 raised to power minus 19. So minus minus 19 will cancel out. So you will have 4.08 divided by 1.6. Oh, sorry, no. 4.08 divided by 1.6. You get 255 electron volts. So furthermore, what we need to do is we need to find out which transition or which level it comes down to. All right. So remember one thing over here. So this represents the energy difference. So this is the energy difference, 2.55 electron volts. So 2.55 electron volts. So this means that minus 3.40 is more negative than whatever this thing is. Okay, so what we need to do is we just simply need to find out the energy level over here. So there are different ways to solve this question. Every student gets confused about what sign conventions to use over here. So remember this one thing. If you have 3.40, you will add that energy difference to get to this level, whatever this is, E2. Similarly, when you have this E2, you will subtract 2.55 to get this level. Okay, so either way, we will get the same answer, so we can actually try this. So E2 minus 2.55 is equal to minus 3.40, or minus 3.40 plus 2.55 will get you your E2. Either way, if you notice that these two are the just the rearranged versions of each other. So 2.55 minus 3.40, you get minus 8.5. Sorry, minus 0.85 electron volts. Okay. Determine the wavelength in nanometer of this radiation as detected by the observer on the Earth. Okay, so what we need to figure out is the redshift, basically. So detected by the observer, we first need to find out what the redshift is. So redshift Z is equal to lambda, change in lambda, difference in lambda over lambda, uh, equals to V over C, right? So have they given us any? Oh, yes, yes, they have given us the speed. So we first need to find out the change in lambda. So V is 6.2 10 raised to power 6. Speed of light is 3 10 raised to power 8. And lambda was 488 nanometers. So we don't need to do this because this is a ratio over here. So 6.2 uh, divided by 3 times by 10 raised to power 6 minus 8 times by 488. So the difference that will come out is 10.0853. So that would mean that observed wavelength will be 488 plus 10.085. So answer plus 488 will be 498. So 498. A value for the Hubble's constant is 2.310 raised to power minus 8 per second. Determine the distance of the galaxy from the Earth. So we already have what we need over here. We have the redshift value. Okay. So we also have the speed. So the Hubble's law basically states that the V is equal to h naught times by distance. So D would be V over h naught. Hubble's constant. V was 6.2 10 raised to power 6. Hubble's constant 2.3 10 raised to power minus 18. So 6.2 divided by 2.3 times by 10 raised to power 6 plus 18. That is 2.695 10 raised to power 24. So you can convert this into two significant figures. So 2.7 10 raised to power 24 meters. Good. All right. Now moving to the next question. State what is meant by the binding energy of a nucleus. All right. So let's see the definition from the our FAQs. Again, this is to show you how you can leverage this great booster pack. So binding energy is the energy required to completely separate the nucleons in a nucleus. Completely separate. So complete. You can also say completely separate to infinity also, right? So we basically so or the work done to do that. So it is the energy required to completely separate the nucleons in a nucleus to infinity. Okay. Table 9.1 shows the masses of two subatomic particles and a polonium 212 nucleus. For the polonium 212 nucleus, determine the mass defect delta M in kgs. So all we have to do is to first find out the mass defect in atomic mass unit, and then since this is 1.66 10 raised to power minus 27 kgs, and then we will multiply with the kg value. So mass defect in U, first we will do number of protons, number of neutrons, sorry, total mass of protons, total mass of neutrons minus mass of nucleus. So we have how many protons? 84 times by 1.007276. And then from 212 minus 84, we have 128, 1.008665 minus 211,942,749. So that's all we have to input over here. So 84 times by 1.007276 plus 128 times by 1.008665 minus 211.942,749. 2,749. So we get 1.77 U. So in kgs, you will multiply this value by 1.66 10 raised to power minus 27. So answer times by 1.66 10 raised to power minus 27. So you get 2.95 10 raised to power minus 27. The binding energy. Oh, so the binding energy, this is in kgs already. So over here, we could do two things over here. We could use the ratio 1 mu is equivalent to 934 mega electron volts, or you could use the E is equal to mc squared. Since we have already have the kg value over here, so we can directly use that. But however, uh, we don't need this one over here because we are finding the energy in the joules. But had the question been in mega electron volts, that's what we would do over here. So E is equal to mass defect c squared. Sorry. So mass defect is 2.9507 10 raised to the power minus 27, and speed of light 3 10 raised to the power 8 whole squared. So answer times by the square of 3 10 raised to the power 8. So 2.6557 10 raised to the power minus 10. So 2.66 10 raised to the power minus 10. The binding energy per nucleon, that would be just simply divided by total number of nucleons. So 2.66 10 raised to the power minus 10. Sorry, 10. I think it was 212. Yes, 212 divided by the total nucleons. So this divided by 212, you get 1.253 10 raised to the power minus 12. So this is this 1.25 10 raised to the power minus 12. On figure 9.1, sketch the variation with nucleon number A of the binding energy per nucleon for values of A from 1 to 250. So this is easy. I'll show you the graph over here. This is the kind of graph that you should draw. It's not like necessary to draw these fluctuations over here, but at least the peak should be somewhere at 56 and it should go this way. So over here, we will draw the graph. So So somewhat like this, where this would be 56. All right, on your line in 9.1, draw an arrow X to show the approximate position of polonium. So polonium would be X over here. Polonium 212 is a radioactive and undergoes alpha decay. Suggest and explain with reference to figure 9.1 why the alpha decay of polonium results in a release of energy. So, so the daughter nucleus resulting from alpha decay would have lower nucleon number but higher binding energy per nucleon. Sorry, binding energy per nucleon. That's why energy is released. Binding. Okay, the last question. Describe how the reflected ultrasound pulses may be used to obtain diagnostic information. Okay, so this is an interesting question which we have also covered. So reflected ultrasound pulses can be used two ways. Their timing and their intensity are both used for different purposes. So, uh, yeah, this one. So the time it takes for reflected ultrasound pulses to return indicates the depth of the internal structure of the boundary, and the intensity or the strength of the reflected ultrasound pulse provides information about the type of the boundary encountered. So time tells us about the depth of the internal structure of boundary. Intensity tells us about the type of the tissue boundary or the nature of the tissue boundary. So we will say that the time delay between uh, transmission and receiving of reflected pulse gives information about depth of the boundary, internal boundaries, whereas the intensity of reflected pulses indicate about nature of the boundary. Define specific acoustic impedance of a medium. So basically Z is equal to rho C. So rho is the density of the mediums. C is not speed of light, it's the speed of sound in that medium. So It is defined as product of density of a medium and speed of sound in that medium. Okay. Table 10.1 shows some data from water and for glass. Determine the intensity reflection coefficient for ultrasound that is incident on a water glass boundary. So we know the intensity reflection coefficient, that is IR over I naught equals to the difference Z2 minus Z1 squared divided by Z2 plus Z1 squared. So we can find out the respective Z values over here so that we don't have to put them up again. So 14, so 1420,000, and then 2500 times by 4560. So we have 11,400,000. So that's what we just have to do. So the difference would be 11,400,000 minus 142,000 squared, and then plus squared. 0,0,0,0,0 plus 142,1,420,000 squared. So answer. So first off, we can find the ratio first, and then we can square the values. So answer minus 142,0,0,0, and then answer plus 142,0,0,0. Once we get this, all we have to do is to do the answer squared. We get 0.606, which is 0.61. So this is the final question of this paper. If you feel that you enjoyed this, if you learned something new, please reach out and tell us what you liked about this. If you feel that I was unable to explain a certain question properly, also reach out. I would love to hear your feedback also. And as before, we have been encouraging you to get this great booster packs because they are going to be helpful to you for articulating the theoretical part of the paper at least. So numerical part you will still have to do, but the definitions, the graphs, the derivations, for that we are here to help you. These great booster packs are available on our Patreon page, so please do go and get those today, and best of luck for your exam tomorrow. Bye bye.